Hello. Welcome to a video about the second half of integrating by Trig substitution. And we're just going to jump right in. So, here is an example where we can use trig substitution. The difference with this example as compared to some of the other ones you might have seen is it's a definite integral. So when we do our substitution, we have to do a substitution for the integrand and a substitution for the limits of integration. So let's jump in. So I have 4x squared plus 9 to the 3 halves. And if you are adding, your trig substitution is going to be the tangent substitution. But what's also different about this one is it doesn't just say x squared plus 9, it says 4x squared plus 9. So when we do our substitution, we are going to call x 3 halves tan theta. The 3 is a nod to that 9, and dividing by 2 is a nod to the 4 that's in front of the x. So we're going to let x equal 3 halves tan theta, which would make dx 3 halves secant squared theta. And I'm going to sneeze. Sorry. All right, so 3 halves secant theta, d theta. Excellent. So when we go to do our substitution, I have the integral of x cubed, which is going to be 27/8 tangent cubed theta, over 4x squared, well, that'd be 9/4 tan squared theta, plus 9 to the 3 halves, times dx, which is 3 halves secant squared theta, d theta. All right, that takes care of my integrand. I can now see why letting x equal 3 halves tan theta was a good idea. Now I got to deal with my limits of integration. So 3 root 3 over 2 is an x value. So what I'm going to do with that, I'll do it in a different color to make it obvious, is if this is an x value, I have to plug it in for x in my substitution. So 3 root 3 over 2 equals 3 halves tan theta, which if I divide both sides by 3 halves, means root 3 equals tan theta. And that would mean theta is 60 degrees, also known as pi over 3. And then if I say 0 equals 3 halves tan theta, I know that theta equals 0. So now I have new limits of integration. That's not a 0. Okay, so I'm set up. I'm ready to go. One of the nice things is I don't have to backtrack now and go back to terms of x like I've had to before. So now that I have a definite integral, I can use those limits once I take the antiderivative. Cool. All right, so now let's try to evaluate this monster. So these 4's divide to make 1. 9's tan squared plus 9 is 9 times secant squared, because tan squared plus 1 would be secant squared. And that's raised to the 3 halves. So this denominator becomes that thing. And then 9 secant squared to the 3 halves means the square root of that cubed. The square root of 9 is 3. 3 cubed is 27. Secant cubed theta. Okay, so I have the integral from 0 to pi over 3. Up top, I'm going to have 81/16 tan cubed theta secant squared theta. I basically combined these two by multiplying. And then in my denominator, after all that work, I have 27 secant cubed theta d theta. So looking pretty good. It's getting condensed here. 81 divided by 27 is 3. I might as well pull that 3/16 out front now. And then secant squared on top and a secant on the bottom would do something like that. All right. So where am I going to go next? Honest to God, I'm not sure. So I have 0 to pi over 3 of tan cubed over secant. Well, if I let u equal tangent, the derivative would be secant squared. Not helpful. If I let u equal secant, then the derivative would be secant tangent, and I don't really have one of those. So you know what? I'm going to go back to the roots and say tangent cubed divided by secant. I should be able to put into terms of sine and cosine. So tangent cubed is sine cubed theta over cosine cubed theta. And dividing by secant is the same as multiplying by cosine. So that's going to look like that, but my cosine will be squared. So then I have 3/16, the integral from 0 to pi over 3 of sine cubed theta over cosine squared theta d theta. So if u equals sine, then du would be cosine, but then my cosine would be on the bottom. If u equals cosine, then du would be sine. I think I'm going to go that route, because if u equals cosine, du is sine, and I can change this sine cubed into a sine squared times sine, and sine squared can be written in terms of cosine. So I think let's go that route and do that. So I have 3/16, the integral from 0 to pi over 3 of 1 minus cosine squared theta sine theta. Sine squared becomes 1 minus cosine squared. So this guy turned into that guy. All over cosine squared theta d theta. So let's let u equal cosine theta, and du would then be negative sine theta. I think I said very quickly, like if u is cosine, du is sine. I meant negative sine. My point was really that if u is cosine, du is in terms of sine. All right. Try not to sneeze again. Okay, so then if we rewrite this, I have 3/16, the integral of, let's see, cosine 0 is 1, cosine pi over 3 is 1/2. Ooh, I'm liking these limits of integration. And let's see, my numerator would be 1 minus u squared times negative du. And then my denominator is just a regular u squared. So I'll pull my negative out in front and then change that to 3/16, the integral from 1/2 to 1, because if I negate the outside, I can reverse the order of integration. And then I have 1 minus u squared over u squared, which is really u to the negative 2 minus 1, which would make my antiderivative, let's see, add 1 to the power, divide by the new power. Antiderivative of 1 is u. And I'm evaluating that from 1/2 to 1. So this is going to be 3/16 negative 1 minus 1 minus 3/16 negative 2 minus a half, which is 3/16 times negative 2 minus 3/16. Let's see, negative 2.5, which would be what, negative 5 halves. So I'll make that a plus. So what have I got? What have I got here? I have negative 6/16 plus 15/32, which is negative 12/32 plus 15/32, which is 3/32. Okay. I do not have my answer key nearby, so full disclosure, I don't know if that's right or not. We're about to find out in real time. Let's check it out. Ooh, I had to zoom out a lot. So let's pull up a calculator, and you can find out with me how well we did. And I say we, but it's really me. You're watching me make this video. So let's see, did Mrs. Vibber make a mistake? Let's see, I'm in radians, which is great. So math 9. All right, what was my original? Let's see, 0 to 3 root 3 over 2. Okay. 0 to 3 root 3 over 2. And now I've got a fraction. X cubed is in the numerator. Oh, I'm in parametric mode. Doesn't make a difference. 4x squared plus 9 to the 3 halves. 4x squared plus 9 to the 3 halves dx. And again, I know it says t. It's fine. Please, please, please be 32.09375. I'm feeling good about this. I'm feeling good. 3 over 32. Yay! We did a big problem and we didn't make a mistake. Woohoo! And you guys are probably thinking, oh, thank God, I don't have to erase anything. Yes. All right. Uno más. One more, one more. What's this next one? Oh, good. No limits of integration. So I have the integral of x over the square root of 9 minus x squared. All right, all right. So let's see. 9 minus x squared. That's going to be a sign substitution. So we're going to say let x equal 3 sine theta. And then dx would be 3 cosine theta d theta. And so I would have the integral of x over the square root of 9 minus x squared times dx. Okay. And so let's see, 9 minus 9 sine squared is the same as 9 times 1 minus sine squared, which is the same as 9 cosine squared. And the square root of 9 cosine squared is 3 cosine theta. Okay, so my denominator becomes 3 cosine theta. Ooh, and 3 cosine theta on the bottom cancels with the 3 cosine theta over there. So this is the integral of 3 sine theta d theta. The antiderivative of sine theta is negative cosine theta. And then it was x equals 3 sine theta. So x over 3 is sine theta. And so if theta, opposite, hypotenuse, adjacent would be 9 minus x squared. So negative 3 cosine theta would be negative 3 times root 3, times root 9 minus x squared over 3. Those cancel. And I just end up with negative 9 minus x squared, square rooted, plus c. Ta-da! This one canceled and was fun. But guess what? We could have done it another way. So when you see these like trig substitution setups, I wouldn't always jump right into trig substitution. You still have other techniques you can try. And if I look at this one, way back up top, I realize, wait a second, 9 minus x squared and x. X is a multiple of the derivative of 9 minus x squared. I could have done this with a u sub. I could have said, well, what if I let u equal 9 minus x squared? Then du would be negative 2x dx. I'm going to multiply by negative 1/2 here. So then this would evolve into the integral of negative 1/2 du over the square root of u, which is really negative 1/2 u to the negative 1/2, which is really add 1 to the power, divide by the new power, which is negative square root 9 minus x squared plus c, which is exactly what we've got. So this was a good example of where trig substitution works and u substitution works. So you can pick whichever you think is going to be easier. And with that, my friends, I am done. Hopefully trig substitution makes sense to you. Have a good one.